Right, so we stop with proxy firewalls. For this type of firewall, clients on the inside of the firewall are usually configured in a special way to associate or connect with proxy instead of the actual end host providing the desired service. Applications capable of operating with proxy firewalls this way include configuration options for it. These firewalls act as multi-home host, and their IP forwarding capability, if present, is typically disabled. So it acts as a multi-home host, and their forwarding capability the IP forwarding capability is usually disabled. Enterprise home inside, outgoing connections terminated at firewall. In the middle, application or service agent for each supported service runs on firewall machine. Internet outside, incoming connections only to running proxy agents. So we see a proxy firewall. Figure 7.2, the proxy firewall acts as multi-home internet host, terminating TCP connections and UDP associations at the application layer. It does not act as conventional IP router, but rather as an ALG. Individual applications or proxies for each service supported must be enabled for communication to take place through the proxy firewall. As with packet filtering firewalls, a common configuration is to have an outside interface assigned a globally routable IP address and for its inner interface to be configurable with a private IP address. While this type of firewall can be quite secure, some people this type is fundamentally more secure than packet filtering firewalls. This security comes at a cost of brittleness and lack of flexibility. In particular, because this style of firewall must contain a proxy for each transport layer service, any new services to be used must have a corresponding proxy installed and operated for connectivity to take place through the proxy. In addition, each client must typically be configured to find the proxy using the Web Proxy Auto Discovery Protocol or WPAD. Although there are some alternatives, so-called capturing proxies, that catch all traffic of a certain type regardless of destination address. In addition, each client must typically be configured to find the proxy, i.e. using the Web Proxy Auto Discovery Protocol or WPAD, XIDAD. Although there are some alternatives, so-called capturing proxies that catch all traffic of a certain type regardless of destination address. The two most common forms of proxy firewalls are HTTP proxy firewalls, RFC 2616, and SOCKS firewalls, RFC 1929. The first type, also called web proxies, work only for the HTTP and HTTPS web protocols, but because these protocols are so popular, such proxies are commonly used. These proxies act as web servers for internal clients and as web clients when accessing external websites. So it acts as the web server that your application requests to, like Google Chrome, and it acts as a client to external websites. Such proxies often also operate as web caches. These caches save copies of web pages so that subsequent accesses can be served directly from the cache instead of from the originating internet web server. Some web proxies are also used as content filters, which attempts to block access to certain websites based on a block list of prohibited sites. So it can be used as a cache as well to save the recently used cache, or it could be used to blacklist prohibited site. This is actually how your IT in your company block website. They use proxy in their operating system or on your Google Chrome. Conversely, a number of so-called tunneling proxy servers are available on the internet. These servers, i.e. PS Siphon, CGI proxy, essentially perform the opposite function to allow users to avoid being blocked by content filters. The SOX protocol is more generic than HTTP for proxy access and is applicable to more services than just the web. Two versions of SOX are currently in use, version 4 and version 5. Version 4 provides the basic support for proxy traversal, and version 5 adds strong authentication, UDP traversal, and IPv6 addressing. To use a SOX proxy, an application must be written to use SOX. It must be SOXified and configured to know about the location of the proxy and which version of SOX to use. Once this is accomplished, the client uses the SOX protocol to request the proxy to perform network connections and optionally DNS lookups. Network address translation. NAT is essentially a mechanism for allowing the same sets of IP addresses to be reused in different parts of the internet. The primary motivation for the creation of NAT was the limited and diminishing availability of IP address space. The most common use case for a NAT is when a site with a single internet connection is assigned a small range of IP addresses, perhaps only a single address, but there are multiple computers requiring internet access. When all incoming and outgoing traffic passes through a single NAT device that partitions the inside private address realm from the global internet address realm, all the internal systems can be provided internet connectivity as clients using locally assigned private IP addresses. Allowing privately addressed systems to offer services on the internet, however, is somewhat more complicated. We discussed this case in section 7.3.4. NAT was introduced to solve two problems: address depletion and concerns regarding the scalability of routing. At the time of its introduction, early 1990s, NAT was suggested as stopgap, temporary measure to be used until the deployment of some protocol with a larger number of addresses, ultimately IPv6, became widespread. Routing scalability was being tackled with the development of classless interdomain routing, CIDR, see Chapter 2. NAT is so popular because it reduces the need for globally routable internet addresses, but also because it offers some degree of natural firewall capability and requires little configuration. Perhaps ironically, the development and eventual widespread use of NAT has contributed to significantly slow the adoption of IPv6. Among its other benefits, IPv6 was intended to make NAT unnecessary. Despite its popularity, NAT has several drawbacks. The most obvious is that offering internet accessible services from the private side of a NAT requires special configuration because privately addressed systems are not directly reachable from the internet. In addition, for a NAT to work properly, every packet in both directions of a connection or association must pass through the same NAT. This is because the NAT must actively rewrite the addressing information in each packet in order for communication between a privately addressed system and a conventionally addressed internet host to work. In many ways, NATs run counter to a fundamental tenet of the internet protocols, the smart edge and dumb middle. To do their job, NATs require connection state on a per association or per connection basis and must operate across multiple protocol layers, unlike conventional routers. Modifying an address at IP layer also requires modifying checksums at the transport layer. See chapter 10 and 13 regarding the pseudo-header checksum to CY. NAT poses problems for some application protocols, especially those that send IP addressing information inside the application layer payload. The File Transfer Protocol FTP and SIP are among the best known protocols of this type. They require a special application layer gateway function that rewrites the application content in order to work unmodified with NAT or other NAT traversal methods that allow the application to determine how to work with specific NAT they are using. A more complete list of considerations regarding NAT appears in RFC 3027. Despite their numerous problems, NATs are very widely used in most network routers, including essentially all low-end home routers support it. Today, NATs are so prevalent that application designers are encouraged to make their applications NAT-friendly. It is worth mentioning that despite its shortcomings, NATs support the basic protocol, like email, web browsing, that are needed by millions of client systems accessing the internet every day. A NAT works by rewriting the identifying information in packet transitioning through a router. Most commonly, this happens for two directions of a data transfer. In its most basic form, NAT involves rewriting the source IP address of packets as they are forwarded in one direction, and the destination IP addresses of packets traveling in the reverse direction. See Figure 7.3. Figure 7.3. A NAT isolates private addresses and the system using them from the internet. Packets with private addresses are not routed by the internet directly, but instead must be translated as they enter and leave the private network through the NAT router. Internet hosts see traffic as coming from a public IP address of the NAT. This allows the source IP address in outgoing packets to become one of the NAT router's internet-facing interfaces instead of the originating host. Thus, to a host on the internet, packets coming from any of the hosts on the privately addressed side of the NAT appear to be coming from a globally routable IP address of the NAT router. Most NATs perform both translation and packet filtering, and the packet filtering criteria depend on the dynamics of the NAT state. The choice of packet filtering policy may have a different granularity. For example, the treatment of unsolicited packets, those not associated with packets originating from behind the NAT, received by the NAT, may depend on source and destination IP address and or source and destination port number. The behavior may vary between NATs or in some cases vary over time through the same NAT. This presents challenges for applications that must operate behind a wide variety of NATs. Traditional NAT, basic NAT, and NAPT. The precise behavior of a NAT remained unspecified for many years. Nonetheless, a taxonomy of NAT types has emerged, based largely on observing how different implementations of the NAT idea behave. The so-called traditional NAT includes both basic NAT and network address port translation, NAPT. Basic NAT performs rewriting of IP addresses only. In essence, a private address is rewritten to be a public address, often from a pool or range of public addresses supplied by an ISP. This type of NAT is not the most popular because it does not help to dramatically reduce the need for IP addresses. The number of globally routable addresses must equal or exceed the number of internal hosts that wish to access the internet simultaneously. A much more popular approach, NAPT, involves using the transport layer identifiers like ports for TCP and UDP query identifiers for ICMP to differentiate which host on the private side of the NAT is associated with a particular packet. See Figure 7.4. Figure 7.4. A basic IPv4 NAT left rewrites IP address from a pool of addresses and leaves port numbers unchanged. NAPT right, also known as IP masquerading, usually rewrites address to a single address. NAPT must sometimes rewrite port numbers in order to avoid collisions. In this case, the second instance of port numbers 23479 was rewritten to use port number 3000 so that returning traffic for 192.168.1.2 could be distinguished from the traffic returning to 192.168.1.35. This allows a large number of internal hosts, i.e. multiple thousands, to access the internet simultaneously using a limited number of public addresses, often only a single one. We shall ordinarily use the term NAT to include both traditional NAT and NAPT unless the distinction is important in a particular context. The address used in private addressing realm behind or inside a NAT are not enforced by anyone other than the local administrator. Thus, it is possible for a private realm to make use of global address space. In principle, this is acceptable. However, when such global addresses are owned and being used by another entity on the internet, local systems in the private realm would most likely be unable to reach the public systems using the same addresses, because the close proximity of the local system would effectively mask the visibility of the farther away systems using the same addresses. To avoid this undesirable situation, there are three IPv4 address ranges reserved for use with private addressing realms: RFC 1918, 10.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. These address ranges are often used as default values for address pools in embedded DHCP servers. See Chapter 6. As suggested earlier, a NAT provides some degree of security similar to that of a firewall. By default, all systems on the private side of the NAT cannot be reached from the internet. In most NAT deployments, the internal systems use private addresses. Consequently, communications between hosts in the private addressing realm and those in the public realm can be facilitated only with participation from the NAT according to its usage policies and behavior. While a large variety of policies may be used in practice, a common policy allows almost all outgoing and returning traffic associated with outgoing traffic to pass through the NAT but blocks almost all incoming new connection requests. This behavior inhibits proving attacks that attempt to ascertain which IP addresses have active hosts available to exploit. In addition, a NAT, especially a NAPT, hides the number and configuration of internal addresses from the outside. Some users feel this topology information is proprietary and should remain confidential. NAT helps by providing so-called topology hiding. As we shall now explore, NATs are tailored to the protocols and applications that they need to support. So it's difficult to discuss NAT behavior without also mentioning the particular protocols it is being asked to handle. Thus, we now turn to how NAT behaves with each major transferred protocol and how it may be used in mixed IPv4 or IPv6 environments. Many of the behavior specifics for NATs have been the subject of the IETF Behavior Engineering for Hindrance Avoidance Behave Working Group. Behave has produced a number of documents starting in 2007 that clarify consistent behavior for NATs. These documents are useful for application writers and NAT developers so that a consistent expectation can be established as to how NATs should operate. NAT and TCP. Recall from Chapter 1 that the primary transport layer protocol for the Internet, TCP, uses an IP address and port numbers to identify each end of a connection. A connection is identified by the combination of two ends. Each unique TCP connection is identified by two IP addresses and two port numbers. When a TCP connection starts, an active opener or client usually sends a synchronization SYN packet to a passive opener or server. The server responds with its own SYN packet, which also includes an acknowledgement of the client's SYN. The client then responds with an ACK to the server. This three-way handshake establishes the connection. A similar exchange with finished FIN packets is used to gracefully close a connection. The connection can also be forcefully closed right away using a reset RST packet. See Chapter 13 for more detail on TCP connections. The behavioral requirements for traditional NAT with TCP are defined in RFC 5382 and relate primarily to the TCP three-way handshake. Referring to the example home network in Figure 7.3, consider a TCP connection initiated by the wireless client at 10.0.0.126 destined for the web server on the host www.isoc.org. IPv4 address 212.110.167.157. Using the following notation to indicate IPv4 addresses and port numbers: source IP, source port, destination IP, destination port. The packet initiating the connection on the private segment might be addressed as 10.0.0.126:9200, 212.110.167.157:80. The NAT/firewall device acting as default router for the client receives the first packet. The NAT notices that the incoming packet is new connection because the SYN bit in the TCP header is turned on. See Chapter 13. If policy permits, which it typically does because this is an outgoing connection, the source IP address is modified in the packet to reflect the routable IP address of the NAT router's external interface. Thus, when the NAT forwards this packet, the addressing is 63.204.134.177:9200, 212.110.167.157:80. In addition to forwarding the packet, the NAT creates internal state to remember the fact that a new connection is being handled by the NAT, called a NAT session. At a minimum, this state includes an entry called a NAT mapping containing the source port number and IP address of the client. This becomes useful when the internet server replies. The server replies to the endpoint 63.204.134.117:9200. The external NAT address using the port number chosen initially by the client. This behavior is called port preservation. By matching the destination port number on the received datagram against the appropriate NAT mapping, the NAT is able to ascertain the internal IP address of the client that made the initial request. In our example, this address is 10.0.0.126, so the NAT rewrites the response packet from 212.110.167.157:80, 63.204.134.117:9200 to 212.110.167.157:80. 157:80, 10.0.0.126:9200 and forwards it. The client then receives a response to its request and for most purposes is now connected to the server. This example conveys how a basic NAT session is established in the normal case, but not how session is cleared. Session state is removed if fins are exchanged, but not all TCP connections are cleared gracefully. Sometimes a computer is simply turned off, which can leave stale NAT mappings in the NAT's memory. Thus, a NAT must also remove mappings thought to have gone dead because of a lack of traffic, or if an RST segment indicates some other form of problem. Most NATs include a simplified version of the TCP connection establishment procedures and can distinguish between connection success and failure. In particular, when an outgoing SYN segment is observed, a connection timer is activated, and if no ACK is seen before the timer expires, the session state is cleared. If an ACK does arrive, the timer is cancelled and session timer is created with a considerably longer timeout, i.e. hours instead of minutes. When this happens, the NAT may send an additional packet to the internal endpoint just to double check if the session is indeed dead, called probing. If it receives an ACK, the NAT realizes the connection is still active, reset the session timer, and does not delete the session. If it receives either no response after a closed timer has expired or an RST segment, the connection has gone dead and the state is cleared. RFC 5382, a product of the Behave Working Group, notes that a TCP connection can be configured to send keep alive packets, see chapter 17, and the default rate is 1 packet every 2 hours, if enabled. Otherwise, a TCP connection can remain established indefinitely. While a connection is being set up or cleared, however, the maximum idle time is 4 minutes. Consequently, RFC 5382 requires Rec-5 that a NAT wait at least 2 hours and 4 minutes before concluding that an established connection is dead and at least 4 minutes before concluding that a partially open or closed connection is dead. One of the tricky problems for a TCP NAT is handling peer-to-peer applications operating on hosts residing on the private sites of multiple NATs RFC 5128. Some of these applications use simultaneous open, whereby each end of the connection acts as a client and send SYN packets more or less simultaneously. TCP is able to handle this case by responding with SYN plus ACK packets that complete the connection faster with the three-way handshake, but many existing NATs do not handle it properly. RFC 5382 addresses this by requiring Rec-2 that a NAT handle all valid TCP packet exchanges and simultaneous opens in particular. Some peer-to-peer applications, i.e. network games, use this behavior. In addition, RFC 5382 specifies that an inbound SYN for a connection about which the NAT knows nothing should be silently discarded. This can occur when simultaneous open is attempted but the external host SYN arrives at the NAT before the internal host SYN. Although this may seem unlikely, it can happen as a result of clock skew. For example, if the incoming external SYN is dropped, the internal SYN has time to establish a NAT mapping for the same connection represented by the external SYN. If no internal SYN is forthcoming in 6 seconds, the NAT may signal an error to the external host. NAT and UDP. The NAT behavioral requirements for unicast UDP are defined in RFC 4787. Most of the same issues arise when performing NOT on a collection of UDP datagrams as arise when performing NOT on TCP. UDP is somewhat different, however, because there are no connection establishment and clearing procedures as there are in TCP. More specifically, there are no indicators such as the SYN, FIN, and RST bits to indicate that a session is being created or destroyed. Furthermore, the participants in an association may not be completely clear. UDP does not use a fourth tuple to identify a connection like TCP. Instead, it can rely on only the two endpoint address or port number combinations. To handle these issues, UDP NOTs use a mapping timer to clear NOT state if a binding has not been used recently. There is considerable variation in the values used for this timer to determine what recently means, but RFC 4787 requires that timer to be at least 2 minutes and recommends that it be 5 minutes. A related consideration is when the timer should be considered refreshed. Timers can be refreshed when packets travel from the inside to the outside of the NOT. Not outbound refresh behavior or vice versa, not inbound refresh behavior. RFC 4787 requires not outbound refresh behavior to be true. Inbound behavior may or may not be true. As we discussed in Chapter 5 and we will see again in Chapter 10, UDP and IP packets can be fragmented. Fragmentation allows for a single IP packet to span multiple chunks, fragments, each of which is treated as an independent datagram. However, because of the layering of UDP above IP, an IP fragment other than the first one does not contain the port number information needed by NAPT to operate properly. This also applies to TCP and ICMP. Thus, in general, fragments cannot be handled properly by simple NATs or NAPTs. Not in other transport protocols, TCP, SCTP. Although TCP and UDP are by far the most widely used internet transport protocols, there are two other protocols for which NOT behaviors have been defined or being defined. The Datagram Congestion Control Protocol, TCCP, provides a congestion control datagram service. RFC 5597 gives NOT behavioral requirements with respect to DCCP, and RFC 5596 gives a modification to DCCP to support a TCP-like simultaneous open procedure for use with DCCP. The Stream Control Transmission Protocol SCTP RFC 4960 provides a reliable messaging service that can accommodate hosts with multiple addresses. Considerations for NOT with SCTP are given in HBA 09 and IDS NAT. NOT and ICMP. ICMP, the Internet Controlled Message Protocol, is detailed in Chapter 8. It provides status information about IP packets and can also be used for making certain measurements and gathering information about the state of the network. The NOT behavioral requirements for ICMP are defined in RFC 5508. There are two issues involved when NOT is used for ICMP. ICMP has two categories of messages: informational and error. Error messages generally contain a partial or full copy of the IP packet that induced the error condition. They are sent from the point where an error was detected, often in the middle of the network, to the original sender. Ordinarily, this presents no difficulty, but when an ICMP error message passes through a NOT, the IP address in the included offending diagram need to be rewritten by the NOT in order for them to make sense to the end client, called ICMP fix-up. For informational messages, the same issues arise, but in this case, Most message types are of query or response or client or server nature and include a query ID field that is handled much like port numbers for TCP or UDP. Thus, a query ID field that is handled much like port numbers for TCP or UDP. Thus, a NOT handling these types of messages can recognize outgoing information, request, and set a timer in anticipation of a returning response. NOT and tunneled packets. In some cases, tunnel packets, see Chapter 3, are to be sent through a NOT. When this happens, not only must a NOT rewrite the IP packet, but it may also have to rewrite the headers or payloads of other packets that are encapsulated in them. One example of this is the generic routing encapsulation (GRE) header used with the point-to-point tunneling protocol (PPTP). See Chapter 3. When the GRE header is passed through a NOT, its called ID field could conflict with the NOT's or with other host tunneled connection. If the NOT fails to handle the mapping appropriately, communication is not possible. As we might imagine, additional levels of encapsulation serve only to complicate a NOT's job further. NOT and multicast. So far we have discussed only unicast IP traffic with NOTs. NOTs can be configured to support multicast traffic, see Chapter 9. Although this is rare, RFC 5135 gives the requirements for handling multicast traffic through NOTs. In effect, to support multicast traffic, a NOT is augmented with an IGMP proxy, see RFC 4605 in Chapter 9. In addition, the destination IP address and port numbers of packets traveling from a host on the outside to the inside of NOT are not modified. For traffic flowing from inside to outside, the source addresses and port numbers may be modified according to the same behaviors as with unicast UDP. NOT in IPv6. Given the tremendous popularity of NOT for IPv4, it is natural to wonder whether NOT will be used with IPv6. At present, this is a contentious issue, RFC 5902. To many protocol designers, NOT arose as a necessary but undesirable wart that has added a tremendous amount of complexity to the design of every other protocol. Consequently, there is staunch resistance to supporting the use of NOT with IPv6 based on the idea that saving address space is unnecessary with IPv6 and that other desirable NOT features, i.e. firewall-like functionality, topology hiding, and privacy, can be better achieved using a local network protection (LNP). LNP represents a collection of techniques with IPv6 that match or exceed the properties of NOTs. Aside from its packet filtering properties, NOTs support the coexistence of multiple address realms and thereby helps to avoid the problem of a site having to change its IP addresses when it switches ISPs. For example, RFC 4193 defines unique local IPv6 unicast addresses, ULAs, that could conceivably be used with an experimental version of IPv6 to IPv6 prefix translation called NPTv6 RFC 6296. It uses an algorithm instead of a table to translate IPv6 addresses to different IPv6 addresses, i.e. in different realms, based on their prefix and as a result does not require keeping per connection state as with conventional NOT. In addition, the algorithm modifies addresses in such a way that resulting checksum computation for common transport protocols (TCP) UDP remains the same. This significantly reduces the complexity of NOT because it does not have to modify the data in a packet beyond the network layer and does not require access to transport layer port numbers in order to operate properly. However, the application that require access to a NOT's external address must still use a NOT traversal method or depend on an ALG. In addition, NPTv6 does not by itself offer the packet filtering capabilities of a firewall, so additional deployment consideration must be made.